In this video cast, we'll look at Chapter 5, Thermochemistry. Thermochemistry has to do with thermodynamics, and thermodynamics has everything to do with energy. Energy in chemistry is measured by the units of joules. Joules are actually a kilogram times a meter squared per second squared. But you don't need to know this, you just need to know that a joule is the standard international unit for energy. Many times we talk in terms of not just joules, but kilojoules as well. Kilojoules are 1,000 times larger than a joule, so there are 1,000 joules in 1 kilojoule. 1,000 J's in 1 kJ. kJ is the symbol for kilojoules. Now, in chemistry, we lots of times talk mainly about a type of energy called heat energy, but there are lots of other types of forms of energy as well, and occasionally we'll see other ones along the way. Heat is the most common one in chemistry, but we also see one called electrostatic as well. And electrostatic energy is used actually to hold atoms or molecules together, and that has an equation of some constant K, Q1 times Q2 divided by D, where Q1 and Q2 are the charges on the ions that are stuck together, and D is the distance between them. Heat energy has several different ways to calculate it, and it's symbolized by the small letter Q. And we'll talk about special situations for heat energy as well, where we actually give it different numbers along the way. So electrostatic and heat are two forms of energy we see in chemistry. Not very often, but occasionally we'll also see the energy of motion. And the energy of motion is sometimes called a kinetic form of energy, or kinetic energy. And this is equal to 1/2 mv squared, where m is mass and v is velocity. So those three types we'll see occasionally in chemistry. We'll see motion only occasionally in chemistry, but electrostatic and primarily heat energy are the ones that we're going to talk about lots in this class. Now, when we undergo a chemical process or a chemical reaction, they can be classified into two forms. The first form is called exothermic. An exothermic reaction is one where it has a negative value of heat, and it is where energy is given off from something to something else. And the other type is called endothermic. And this one has a positive value because it's where energy is taken into something. Now, to know the something that is either giving off energy or taking in energy, we need to make a definition. We need to define something called the system that we're looking at versus the surroundings that are always around it. And in chemistry, lots of times we look at atoms, molecules, or ions that are inside of a beaker or a flask or exist in some container. The system is those atoms or molecules or those ions, and the surroundings is the beaker or the container or any air that's around them, or any type of gas that surrounds those things. And so when we talk about endo and exothermic, we always say exothermic is from the viewpoint of the system, from the atoms, molecules, or ions. And when they give off energy, they have a negative sign or a negative value for the Q, or the heat, and the surroundings gain that energy. The beaker, the container, the air, or a real common one is the thermometer that's stuck into the system. And therefore, exothermic reactions, when they're measured with a thermometer, have a raise in temperature, or temperature goes up. Right? Endothermic reactions, on the other hand, generally have a decrease in temperature. Temperature goes down. So knowing the difference between a system and a surroundings is key throughout this entire chapter. Remembering that the system is the atoms, molecules, or ions that make up the reaction or the process that's happening, and the surroundings are the beaker, the container, the air that's around them, the thermometer that's measuring them, whatever's holding them, that type of thing. And knowing the flow of energy, endo or exothermic, from the system to the surroundings or the surroundings to the system is key. Let's look at some of the sample problems throughout the text in Chapter 5. First of all, on page 169, the question is asked, what are the terms for the energy an object possesses? Because of its motion, well, we call this kinetic energy or energy of motion. And remember, the equation for that is 1/2 mv squared. And because of its position, it's actually called potential energy. And if it's potential energy that's based on how high something is, it's equal to mgh, where this is mass, this is gravity, and this is height. We don't see these two types of energy too often in chemistry. You'll see them a lot more in physics when you talk about moving objects. Although we do have lots of moving objects called atoms, molecules, or ions, but we usually don't measure the potential energy of those. We usually measure the kinetic energy of gases, but not nearly as often. But you should be familiar with those terms of energy as well. Second question is, what terms are used to describe the changes associated with temperature change? And temperature change, if temperature goes up and it's measured by a thermometer, we generally say that the reaction was exothermic. And if temperature goes down, we generally say that the reaction was endothermic, or it took in energy. And therefore the surroundings lost some energy, because remember, the thermometer is part of the surroundings. What term describes a change associated with a moving object? Well, we say that there was a change in kinetic energy or a change in potential energy. And we say that if it stopped moving, it doesn't have kinetic energy anymore. And of course, if it speeds up, it has more kinetic energy because it's energy of motion. Systems versus surroundings. We talked about that just a little bit. And if I draw a beaker and I'd put some atoms inside of the beaker or some molecules, I'd say that the system is the atoms or the molecules or the ions that are inside of that beaker. And the beaker itself and the air around it are the surroundings. They are the surroundings. And keeping the system and the surroundings straight are super, super key and important. Many times in chemistry we talk about something called the internal energy of the system. And the system, of course, atoms, molecules, or ions, will have a certain amount of internal energy, and many times it's put in a graphical format where we have energy here on the vertical axis, and then we have the reactants down here and the products up here. And if the products are gaining energy, we'll go from reactants to products with a big arrow like this. If the products are losing energy and the reactants are gaining energy, we'd have an arrow going in the other direction. If we had this bold arrow that's going up this direction, we'd say that the internal energy of the system is increasing. The delta E, or the change in the internal energy, would be positive. And you should be able to look at a graph like this and say, oh yeah, there's energy being gained or there's energy being lost by the system. The next page has a couple more questions, and it says, determining the sign of delta H. Well, before we can answer this question, we need a little bit more terminology. In chemistry, we usually talk about something that we said before is called heat energy. And heat energy we symbolize by the letter Q. Now, if we have heat energy at a constant pressure, in other words, it's in a beaker that's open to the atmosphere, where we're not squishing something or changing it or allowing it to be compressed, as long as it's at constant pressure, we give this heat at constant pressure a new name. We call this heat at constant pressure the enthalpy. And the enthalpy is the heat or energy of a reaction that's either lost or gained. Now, enthalpy has its own special letter. Remember how we used Q to represent heat? Well, heat at constant pressure is called enthalpy, and it's symbolized by the triangle H. The triangle is actually the Greek letter delta, and it means change, and H stands for enthalpy. So H stands for enthalpy, which is nothing more than heat at constant pressure, and the triangle stands for change. And we want to look at the change in enthalpy. So let's answer a couple of questions now about the enthalpy change and whether it's negative or positive for some chemical processes. Indicate the sign of the enthalpy change for each of the processes carried out under atmospheric pressure and indicate whether the process is endothermic, meaning taking in energy, or exothermic, meaning giving off energy. First of all, an ice cube melts. Well, if you have an ice cube and you have it at room temperature, the ice cube will melt. And the reason it melts is because energy from the surroundings are going into the system. That's if we define the ice cube as the system, which is, what it's asking about. And since it's absorbing energy, we would say that, or since the system is absorbing energy, it would be a positive change in enthalpy, or it would be an endothermic process. An endothermic process, because energy is taken in by the system, which is the ice cube, and the energy is lost by the surroundings to melt the ice cube. Letter B says 1 gram of butane is combusted in sufficient oxygen to give complete combustion of carbon dioxide and water. So butane is C4H10, and if we combust it in oxygen, we're going to get some carbon dioxide and some water. And if you've ever been around something that's been ignited on fire before, you know that when you put your hands near that thing that's ignited on fire, there is some heat, or it feels warm. Since the system is the butane, and we, when we're standing around the fire feeling the heat, are the surroundings, we would say that this process would have a negative enthalpy change, and therefore it would be an exothermic process, or in this case, an exothermic reaction. Well, the next question asks about a system that is closed, or inside of a container. And it says, suppose we combine 1 gram of butane with sufficient oxygen to completely combust it inside of a cylinder. Now, the cylinder they're talking about here is one that's shaped a lot like on page 170 of your textbook. It looks like this, and some people call it a piston cylinder, because we have a movable portion of the top of the cylinder. That's why they have this little post right here, because it can move up and down. And inside of this container right here, we're going to combust some butane. And the question continues on and says, a spark initiates the combustion of butane, which forms carbon dioxide and water vapor. If we use this apparatus to measure the enthalpy change of the reaction, would the piston rise, fall, or stay the same? Well, when we combust this, of course, we're going to take and we're going to change it into carbon dioxide gas and water, and we're going to give off some energy. That energy, I'm going to just draw a crude picture of this piston here. That energy that's released would push against the movable piston and move it up. And so we'd say that the piston would rise when we combust something inside of the piston. We can represent something like this reaction up here with the combustion of butane as something called a thermochemical equation. A thermochemical equation is just like we've learned to write equations before. C4H10 plus O2 goes to CO2 plus H2O, except now at the end of the equation, and I should balance this equation first. I think I'm going to need I believe it's an 8 here, and let's see, a 5, a 10 here, and that gives me 10 plus 16, that's 26, so 13 here, and then I need a 2 here as well. So at the end of this balanced chemical equation, you put a symbol of triangle H, meaning what is the enthalpy change for this reaction. And of course, we talked about how this reaction would be an exothermic reaction, and so I'll just make up a value right now now and say that this exothermic reaction would give off 500 kilojoules. Now, the thermochemical equation can become very, very valuable because it relates the coefficients in the balanced chemical equation to the amount of energy gained or lost. For every 10 moles of water that are produced, 500 kilojoules of energy are given off. For every 8 moles of carbon dioxide that are produced, 500 kilojoules are given off. For every 2 moles of butane that are combusted, 500 kilojoules of energy are given off. And so you can see that the coefficients right here, all the way along, are related to the amount of energy that's released. Related to the amount of energy that's released. Generally, not always, but generally, a thermochemical equation is written so there is a 1 in front of the first thing, or the thing in question that's being combusted. And so lots of times you might see this equation balanced a little bit differently than what we learned before. There'd be a 1 here in front of the butane. There'd be 4 here in front of the carbon dioxide, and a 5 here in front of the H2O. And then you say, yeah, but now there's not a whole number here, because to balance this you'd have to have 6.5. But many times thermochemical equations are balanced so you can have a 1, or the number coefficient 1, in front of the object or the chemical in question. And if you have to use a half or a quarter or a third or something like that, you go ahead and do it. And the same relationships then would apply. 1, 2, and since actually I took these, I put this example of 500 kilojoules down for 2, 13, 8, and 10. If it were actually measured as 1, 6.5, 4, and 5, it would be negative 250 kilojoules given off, because it would be half as much, because I'd have half as many moles of each thing. Because as we'll learn in the next video cast, the amount of energy that's released is totally proportional to the amount of substance that we combust or have undergo a chemical process. And so for every 1 mole of this stuff that's burned, 250 kilojoules will be given off. Remember, this is just an example. This is an example. It's not what the true enthalpy of this reaction is. I don't know exactly what it is offhand right now. We'll continue the next video cast with these Give It Some Thought questions that continue on page 8. Until then, good luck with your thermochemical diagrams and enthalpies.